All right, so let's take a look at this circuit. This circuit is an example of negative feedback. That's what this title is called. Feedback, specifically negative feedback, just means we take our output and we feed it back to the negative input. That's the definition of negative feedback here. But what's actually happening in this circuit? Okay, so let's take a look at it. I've got ground here, and I have a voltage source with a voltage drop of V in or VI across it. So I know that my plus terminal is going to be at VI. Well, according to the golden rules of op amps, my two input terminals have to be at the same potential. So that means that my minus terminal has to be at a voltage VI as well. And well, since my minus terminal is connected directly to my op amp output, that means that my output voltage has to be VI as well, right? Right here, my input is directly connected to my output. That is what negative feedback is. And so I want to just go over what's happening practically in an op amp, which is the reason why we can see why we need a very large gain, or why it's desirable for AOL to be very large, and why, as a result of a very large open loop gain, we do get to make the assumption that these two voltages at the inputs are close to identical, and that makes all of our math very easy for solving these op amp problems. So let me go ahead and just write out what I see in this circuit. I know that for a general op amp, the output voltage is going to be equal to the open loop gain multiplied by the voltage at the plus terminal minus the voltage at the minus terminal, right? Well, in this case, I have my open loop gain multiplied by what voltage is at my plus terminal? Well, it's going to be VI. And what terminal voltage is at my minus terminal? Well, it's going to be whatever V out is, right? My voltage at my minus terminal, it's equal to V in, but it's also equal to V out, okay? Based on this equation here. And so if I were to go ahead and solve this equation for V out, let me go ahead and do that. I would get V out is equal to AOL times V in minus AOL times V out when I FOIL, right? Let me actually get rid of these. I don't need those. I can add the AOL times V out term over to the other side and then factor out a V out so that I get 1 plus AOL is equal to AOL times V in. I can divide this term over to the right side so that I get AOL times V in over 1 plus AOL. And now I can divide the top and bottom, or multiply by 1 over AOL. And I get that V out. So here this AOL and this AOL cancel. And then on the denominator, I get an AOL and an AOL that give me a 1, and then I just get a 1 over AOL. And that's what I'm left with, is this equation right here. And so you can see that in such a circuit, so this is the ideal case here where I'm assuming that my inputs are equal, right? V in at the plus terminal, V in at the minus terminal. And what I get is that my output is equal to my input. Well, if I take a look at this case, the case where I just derived this equation for V out, what condition is going to give me V out is equal to V in? Well, it's the condition that AOL tends to infinity, because if AOL goes to infinity, this term goes to 0, and I'm left with V out equals V in, right? So that's why it's desirable for us to have a large open loop gain, because then I can actually treat my two inputs as equal, and that's what we want. That makes solving the circuits easy, okay? And so let's just say I had an example here where AOL is, let's just say it's 100,000, something like that, and then let's say that V in is 5 volts, and I want to know what is V out in this case. Let's go ahead and plug it in. V out is going to be equal to 5 volts divided by 1 plus 1 over 100,000, which is going to be, let me go ahead and throw that into my calculator, 5 divided by 1 plus 1 over 100,000. I get 4.999950001 volts. Okay, and so that's what I'm looking at here in a practical circuit, which doesn't have infinite open loop gain. Like my gain's 100,000. So instead of getting 5 volts at the input and 5 volts at the output, I'm getting 5 volts at the input and 4.99995 volts at the output, right? And so that, since my output is actually connected back to my input, that is also the voltage at my minus terminal. And so my voltage in a non-ideal op amp may not be 0 between these two nodes, but it's pretty close. So what is it? So if my input is 5, Vp minus Vm is equal to 5 volts minus 4.99995. Let's just say 5, that's my voltage. That difference, I'll just call it delta V in, is equal to, and let me just do 5 minus the answer. It's going to be 49.99 microvolts, or 49.99 times 10 to the minus 6 volts, which for all intents and purposes is basically 0. For solving circuits, it is an okay approximation if my open loop gain is large enough. It's an okay approximation to say that these two terminals are at the same potential. Okay, that's my slide on negative feedback. That pretty much wraps up the laying of the brickwork for op amps. And now in the next couple of slides, we're going to go ahead and look at some of the most popular op amp topologies, how to derive the equations for them, and then how to solve problems involving op amps, and how to find output voltages and determine the currents flowing and all that good stuff we've been doing all class long. All right, so I'm going to go ahead and end this video right here.